In this video, we'll learn about Contrastive Hebbian Learning, or CHL for short. This video was produced in Korean and then translated into English. The audio was generated by AI, text-to-speech. In Chapter 1, we looked at the Hebbian learning rule. And in Chapter 4, we looked at the Contrastive Divergence algorithm. The CHL discussed in this chapter is based on the Hebbian learning rule and the Contrastive Divergence algorithm, which has been used to train a variety of energy-based latent variable models. In 2003, Xiaohui and Sebastian Seung showed in their paper Equivalence of Backpropagation and Contrastive Hebbian Learning in a Layered Network that CHL is equivalent to the backpropagation algorithm commonly used in deep learning. In this video, we'll take a closer look at the CHL learning algorithm and implement a simple CHL model to classify MNIST images. We want to train such a multi-layer neural network using Contrastive Hebbian Learning. This network consists of an input layer, multiple hidden layers, and an output layer, just like a typical feed-forward network. This is an example of a network for performing classification. The input features are fed into the input layer, and after passing through multiple hidden layers, the final classification results are output in the output layer. Here K is the layer number. In this figure, the kth layer has 4 hidden neurons. Let the activation value of each neuron in this layer be xk. To obtain the output layer's results during training and prediction, we need to first determine these values. In a typical feed-forward network, xk is computed in this way. And as W and B are updated by backpropagation, xk gradually converges to an appropriate value. But since we won't be using backpropagation, we need to determine xk in some other way. We want xk to start from some initial value and converge to some reasonable value v. For example, we want xk to converge to a constant value v along this curve. Such a curve can be expressed as follows. The x-axis is the time step t, and the y-axis is the value xk. If t is repeated infinitely, xk becomes v. Differentiating both sides of this equation with respect to t gives us the following expression. Since the right side of this equation is minus xk plus v, this equation can be written as follows. This is a differential equation for the function xk of t. The solution to this differential equation is the function xk above. Now, let's use a function f of x instead of the constant v on the right side of this equation. And let's define the function f of x as follows. For example, let's describe the activation value of this neuron. The activations in the lower layer are multiplied by weights and added together. This is the first term on the right-hand side of this equation. Then, the activations in the upper layer are multiplied by transposed weights and added together. This is the second term representing the feedback signal. Here, gamma is the feedback gain, which is a hyperparameter that controls how much the feedback signal affects the xk. Finally, a bias is added. In general, f is a sigmoid function. In this differential equation, as t repeats infinitely, xk will gradually converge to this activation value. This is a first-order nonlinear ordinary differential equation. This type of equation can be challenging to solve in general. In this case, finding an analytical solution is impossible, and numerical methods are necessary. Euler's method, or other numerical techniques, can be used to approximate the solution. Using the forward Euler method, an approximate solution to this equation can be expressed as follows. The left side of this equation is delta xk, and the delta t is forward Euler method's time step. Contrastive Hebbian learning is based on the contrastive divergence algorithm. This means that learning takes place in two phases. In the forward phase, the input is presented and the output is built by forward propagation of neural activities. In the backward phase, the outputs are clamped and the activity is propagated backwards towards the input layer. The initial value xk0 is updated to xk1, and in the next time step, xk1 is updated to xk2. If we repeat this, xk's will converge to the appropriate values. Next, let's take a look at the learning algorithm for CHL. Let's take a multi-layer neural network like this as an example. This neural network consists of a total of 5 layers. 1 input layer, 3 hidden layers, and 1 output layer. K is the layer number from 0 to 4. L is the number of the last layer. Every layer but input layer has biases, and each layer is connected by weights. This structure is identical to that of a typical feed-forward network. The activations of each layer in the forward phase are denoted by x-check k, and the activations of each layer in the backward phase are denoted by x-hat k. X-check 0 and x-hat 0 represent input data. X-check L is initialized to 0. X-check LT represents the final outputs of the network, i.e. the label or target data predicted during the forward phase. X-hat L is the fixed target data, and the outputs of hidden neurons are also initialized to 0. The weights and biases of each layer are randomly initialized. First, perform the forward phase. Iterate over t from 1 to t with step dt. Iterate over k from 1 to L. Compute the forward outputs x-check k at time step t for all layers except the input layer. When t is 1, x-check k-1, t-1 is the fixed input data. It is not updated during the iteration. When k is 1, the above expression becomes as follows. And when k is 4, it becomes as follows. Here x5 and w4 do not exist, so they are both 0. Next, perform the backward phase. Iterate over t from 1 to t with step dt, the same as the forward step. This time, we iterate over k from 1 to L minus 1. In the right figure, k is repeated from 1 to 3. For each hidden layer, compute the backward outputs x hat k at time step t. The input and output layers are not updated. In the backward step, x hat 4 is clamped as the label or target data. As the iteration progresses, the x hat 4 signal is backpropagated to the lower layers. Finally, at the end of the two phases, we update the weights and the biases based on the following rules. As we saw in the previous video, the learning rule for RBM using contrastive divergence is as follows. The learning rule for CHL is also similar to this. Again, in the backward phase, the desired target data is clamped and backpropagated to the lower layers. This corresponds to the first term of this equation, Hebbian learning. In the forward phase, the target data estimated by the model is propagated to the lower layers. This corresponds to the second term of this equation, anti-Hebbian learning. The same goes for biases. Next, let's implement a simple CHL model for MNIST classification. Load the MNIST dataset, one-hot encode the target data, and generate training and test data. The structure of the network is as follows. The input layer has 784 neurons, and the output layer has 10 neurons. There's one hidden layer with 128 neurons. The learning rate eta was set to 0.01, and the feedback gain gamma was set to 0.5. The number of neurons in each layer of this network is as follows. L is the last layer number 2. The number of epochs was set to 10, and the batch size of the data being fed to the model was set to 10. The simulation time t was set to 10, and the forward Euler method's time step dt was set to 0.5. We randomly initialized the weights and biases. Write a function that performs the forward phase. It takes input data and generates output for each layer according to the algorithm we looked at in the previous slide. Next, write a function that performs the backward phase. It receives input data and target data and generates the output of the hidden layer. Next, we generate batch data, perform forward and backward phases, and update the weights and biases. Repeat this process several times. This is the learning process of CHL. Finally, we feed the test data into the trained model. And we use the final output of the model to measure the accuracy on the test data. The results are as follows. The accuracy was about 97%. In this video, the accuracy was around 64% when simple Hebbian learning was used. You can see that CHL significantly improves the accuracy. Let's run this code. we got the following results. In this video, we looked at contrastive Hebbian learning. In the next video, we'll explore a competitive learning model using Hebbian learning.